All right, so let's talk about some new stuff now. Let's get into aldehydes and ketones. So this is kind of the back half of chapter 12. Now, what makes aldehydes and ketones kind of unique and different is we're introducing a new functional group. That new functional group is called a carbonyl group. Carbonyl group is featured by a carbon double bonded to an oxygen somewhere in the chain. So I've got my chain of carbons, and somewhere in that chain is the carbonyl group. Carbon double bonded to oxygen. Now, depending upon the location of that carbonyl group, we can get some different kinds of substances. If that carbonyl group is on the end of a chain, that's what is called an aldehyde. If that carbonyl group is in the middle of a chain, that's what's called a ketone. Now, what makes these particular compounds kind of interesting is think back to that idea that we had about electronegativity, polarity. The bond here is very polar. And so we've got this negative side here around the oxygen and this positive side around the carbon. And so we can generally think of that carbonyl as being a polar piece in an otherwise non-polar structure. And so because of this, again, depending upon size, carbonyls, substances that have these carbonyls tend to have more polar properties than others. But that polarity is limited in some ways. Similar to what we saw with alcohols on Tuesday, the longer that chain length gets, the more nonpolar that molecule is based on the carbon chain, the less impact that polar group is going to have. So we saw that with alcohols. We're going to see similar kinds of things with aldehydes and ketones. Like I said, depending upon the location of that carbonyl group, we can split carbonyls into two different subcategories. If the carbonyl group is on the end of the chain, we refer to that group, that molecule, as an aldehyde. And so if you kind of think about, how we were phrasing things, we talked about alkanes, and alkanes kind of had their own, structure and identity to them. We talked about alcohols, and alcohols we recognize as kind of that first functional group, and that first functional group made us change the ending of the name of the chain accordingly. Aldehydes and ketones do the same thing. And they actually have a kind of a higher precedent than alcohols do. So if I have an aldehyde and an alcohol present, I would change the name of the substance to the aldehyde ending, not the alcohol ending. If that carbonyl group is anywhere in the middle of the chain, so pretty much just not on the end, then we're talking about a ketone. Some cosmetic kinds of things come up here. Now that we start to see other atoms, things besides carbon and hydrogen in the chain, it becomes important for us to try to recognize how to write that in terms of an expanded structural formula. And this is how we do it. So for aldehydes, in that expanded structural formula, we would mark them as CHO. And we don't have to show the double bond there because it'd be generally understood that if it's at the end, it's got one bond to carbon, and since it only has the one hydrogen, it's got one bond to hydrogen. We know that carbon forms 4 bonds in total. Well, if those 2 bonds are spoken for, then the other 2 bonds must be to the oxygen. For the ketone, again, we're looking at this keto group, this carbonyl in the middle, and we see it's just going to be written as CO. So CO in the middle of a chain would indicate a ketone in that chain. Because, again, if I'm in the middle of a chain, that carbon is attached to 2 other carbons. And so since carbon makes 4 bonds, the other 2 bonds must be to the oxygen, since there's no hydrogen there as well. If it was COH in the middle, then we would know that we're talking about an alcohol, not a ketone. Because again, it has to come from somewhere. We have to have something going on there otherwise. We've got to get to 4 bonds on the carbon. All right, so let's look at each of these here, and let's just do a very simple classification. So I'm going to classify, I'm going to mark all of the aldehydes here in yellow. I'm going to mark all of the ketones here in blue. So somebody give me an example of an aldehyde. Which one of these is an aldehyde? Right, B. B is an aldehyde. How do I know that it's an aldehyde? Well, I've got the carbonyl group here on the end of the chain. So there's carbon on one side, but not on the other. That's an aldehyde. Are there any other aldehydes on this page? C. Okay, same reasoning. Now, what about ketones? Okay, A is a ketone. What about D? Is D a ketone? It is. Only thing that is making it different is that its chain isn't a linear chain. It's a cyclical chain. And so any kind of ring structure that has this carbonyl group on it would also be a ketone. And that would include even benzene rings. So if I have a benzene ring with that double bond on it, works out the same way. Now, you won't actually see that because now that you do the math in your head, you go, well, hold on a second. Each carbon in the benzene ring has 3 carbon bonds. There's no room for a double bond to oxygen. But any kind of ring structure that has this carbonyl on it would indeed be a ketone. All right, All right, let's go to everybody's favorite thing to do when it comes to organic chemistry. Let's figure out how to name this stuff. Okay, two different naming systems in play here. And we're going to kind of see both because both are very commonly used. So the official naming system, the IUPAC system, involves changing the name of that longest chain and changing the ending to AL. So, as far as like proper pronunciation goes, we'd be talking about methanal, ethanal. We're going to really hammer that al at the end instead of all, because we don't want to confuse it with an alcohol. The way that you're probably more familiar with is the common version. The common version just calls it aldehyde at the end. And the kind of aldehyde that it is based upon how many carbons are in the total chain. Unfortunately for us, the common naming system uses a completely new set of prefixes, unlike any of the ones we've seen thus far. Now, there's some similarities, but not that much. So instead of, mono or meth, like what we've seen for one, we get form. So the one carbon aldehyde is formaldehyde. Probably have heard of it. Two carbons, the prefix is acet. You've seen this in other places. Acetylene for the two carbon alkyne. Acetic acid for the common ingredient in vinegar that makes it smell so great. We've seen it in other places. It means a two carbon chain. So acetaldehyde would be the name of that two carbon aldehyde. For 3 and 4, kind of close. We're familiar with prop for propane, propene, propyne, propyl groups. We're familiar with butyl for 4 carbon chains. These are just variations on those. Propion aldehyde would be a 3 carbon aldehyde. Butyr for butyraldehyde or butyraldehyde, depending upon just kind of how you pronounce that Y. So more often than not, for one of these first 4 aldehydes, you can see either combination being used. And both would be considered acceptable. So if you had just a simple 4 carbon aldehyde show up in your mastering chemistry and it asked you to name it, you could go with either system. You could call it butanal, which would be the IUPAC name, because it's 4 carbons, so that's butan, and al at the end. Or you could call it butyraldehyde. And I believe mastering would accept either one, because they're both considered common enough to be considered correct. Now, beyond the first 4, then we need to get into kind of our more conventional system that we've been kind of hammering these past 2 weeks. Look at the carbon chain, attach the appropriate prefix, and end it with that AL. So here's kind of the comparison of those two. Methanal, ethanal, propanal, butanal for the IUPAC names, or formaldehyde, acetaldehyde, propionaldehyde, or butyraldehyde for those first 4 in the common system. And honestly, even more commonly, it's those first two that are probably the most commonly found, where we see their usage the most often. Okay. Now, what do we do with a problem like this? Give the IUPAC name for the following aldehyde. Well, we handle it the same way we always have. Start with that longest chain, recognize that we have an aldehyde here, and we're going to just kind of start from there, and then we'll see if there's anything else on the side. So I'm going to break out the highlighter here again. Here's my longest chain. And I can see that in that chain, I've got this aldehyde group on the end. How many carbons are in this chain? 5. So I've got 5 carbons. So that would be pent, pentan, since we're talking about all single bonds. And with that aldehyde group there on the end, this is pentanal. Now, the naming for aldehydes assumes that that aldehyde is in the 1 position. So as far as numbering this, there's no ambiguity. It's not a left to right versus right to left thing. It's a where is the aldehyde group? That's number 1. So this is 1. This is 2. This is 3. This is 4. And this is 5. And there's no other way to number it. This doesn't branch off into other chains. This doesn't do anything else. And we have to label that aldehyde group with 1. So what's hanging off of here? What do we call that CH3 side group? Methyl. So this is methyl. And where is it? It's on carbon number 2. So this is 2-methyl. There are no other side groups, so I just put the names together. 2-methyl pentanal. All right. Questions, thoughts, confusion? All right, let's move on. All right, ketones. Ketones, very similar. Again, the ketone is going to take kind of a higher order than an alcohol group or a methyl group or a fluoro group, to the point where we change the name from E to ONE. So a 5-carbon ketone would be pentanone. A 3-carbon ketone would be propanone. Now, there are some common names. Those common names are similar to the kind of names we did with ethers. Remember, with ethers, we just named the 2 things on either side of the oxygen, and we put them in alphabetical order. Ethyl methyl ether, diethyl ether, methyl propyl ether. Well, The common system for naming ketones is the same way. You kind of divide the molecule into groups based upon the carbonyl, and then you just name what's on each side of the ketone carbonyl group. So propanone here becomes dimethyl ketone. We know it better as acetone. For butanone here, it's ethyl methyl ketone. For 3-pentanone here, we've got ethyl, so diethyl ketone would be the appropriate common name. For cyclic ones, there really isn't a common name for them, because if the ketone is in the middle of a ring, there's no way to separate it into sides. Now, you might be asking, well, why do we have to put 3 for pentanone here, but we didn't have to put a number for butanone or propanone? Well, this comes back to a point we've made a couple of other times. If the location is ambiguous, that must mean that it's the only way to draw it. So if I don't give you a number, must mean that there's no way to number it where you would get a different result by changing the numbering. For propanone, that ketone group, that carbonyl, can only be on the second carbon. Can't be on the first, can't be on the third. That would mean they are aldehydes, not ketones. It has to be in the middle. For butanone, can only be on the second carbon. Now you say, well, it's shown on the third carbon there. Not if you number it the other way. It's on the second carbon if you label it the opposite direction. So in those cases, since the only option is 2-propanone and 2-butanone, we don't need to say the 2. We already know where it's going to be because it can't be anywhere else. But once that location of the carbonyl is no longer arbitrary, then we have to start giving details about location. Because in pentanone, it can be in this third position in the middle. It could also be in this second position. They would be 2 different substances. All right, let's take a look at another example. So using the IUPAC system, so again, same way from the common system. Common system here would be a little bit more complicated than what we would want to get into. So in this case, we have 2 different possible longest carbon chains. Because this branching here would rise to 2 different possibilities for the longest chain. Good news for us, however, those 2 chains happen to be the same length. So choosing one over the other really doesn't make a difference. But one thing we always want to be careful about, if we see branching near the end of a chain, We want to make sure that we kind of do our due diligence and count out that chain as an alternative to just the one that goes straight across. Because sometimes what we'll find is that that extra branch ends up making the chain longer. You know, just as an example, both of these are 5 carbon chains. Let's just say, for the sake of argument, that instead of CH3, this was CH2, CH3. Okay. A little bit ahead of ourselves there, aren't we? Yeah, it has been. Well, if this were the case, well, then we could see that by taking this side branch here, we would end up with 6 carbons in the chain instead of 5. That would make it the longest chain instead. We always focus on the longest when we're trying to figure out how many are in the chain to figure out the numbering system. Now, like I said, in this instance, it didn't matter. The chains ended up being the same size anyway. So recognition here, we've got a 5 carbon chain. So we're dealing with pentanone because we've got that ketone group, the carbonyl there. Once again, the numbering system is going to favor the carbonyl group. So unlike the aldehyde, where there was only one way to number it, we started at the aldehyde. Here, there is a possibility of numbering both ways, but we need to choose the numbering system that gives us the lower number on that carbonyl group. So the bottom set is where we're going to go, which means that this is 2-pentanone. And we've got this methyl group here on the 4th position. So this is 4-methyl. Put those together. It's 4-methyl, 2-pentanone. All right, questions with this example? All right, I want you to try these ones then. So I've got 2 ketones here. I want you to name these 2 ketones. Give you a couple of minutes to work through it. We'll come back and we'll look at the answer here in a minute. All right, let's see how we did. So in the first one, there were no side groups on it. So it was just a 6-carbon chain. And so it became a matter of recognizing, okay, with 6 carbons, we know we're dealing with a hexanone. And then the location of the carbonyl group would be on the 2nd carbon if we numbered it backwards. So 2-hexanone would have been the correct answer. For letter B, we have a 4-carbon chain. So this is a butanone. From a numbering perspective, again, we number favoring the carbonyl. So that would also mean right to left. The group on the end is a chloro group. So this would be 4-chloro, 2-butanone. Yes, Sean. Is benzoyl chemistry related? Okay. No. Oh. So if we're talking about the motor oil, well, not in the way that you're thinking. Okay. All right. Other questions? Okay, so the only time we wouldn't have to put the number in is if the location of the carbonyl group was obvious. In this case, that carbonyl group, it could be here, but it could also be on one of these interior carbons as well. And if it were, then it wouldn't be 2-hexanone, it would be 3-hexanone. So we need to signify the number so that we can know where that group is. In the case of butanone, that butanone is, well, technically, if there wasn't a chloro group there, then we would be able to talk about that group could be here or here, and they would both be 2. The reason we had to put the 2 there with the 4 is because now that we've introduced this extra side group, now the numbering is not ambiguous. Calling this 4-chloro-2-butanone signifies a difference compared to, if I just called this 1-chlorobutanone, that could imply that the chloro group is next to the carbonyl group, and it's not. So since the molecule name and structure is not obvious anymore, we use numbers to clarify positions. When the location is obvious, meaning it can't be anywhere else, then putting the number in doesn't matter. So in the first example, it matters because that carbonyl group could be there. It could also be on one of the carbons further in, and they would have different names. Here, it's not obvious because of the fact that we've got that chloro group there as well. And the location of that chloro group relative to that carbonyl requires that I number both of them. Other questions? All right, let's talk a little bit about solubility then. As we mentioned when we brought up the idea of the carbonyl in the first place, those carbonyls are going to create polar groups inside of that carbon chain. And since water is polar and we have these polar groups on these ketones and aldehydes, we're going to see, because like dissolves like, things that are polar dissolve in other polar things. We're going to see that there is going to be some solubility with aldehydes and ketones that we wouldn't have expected with other organic compounds. Thus far, mostly what we've talked about is if you've got a hydrocarbon, it doesn't dissolve in water. Well, with the introduction of this oxygen into the compound, now we're seeing that there is some solubility there. And again, like what we saw with the alcohols, that solubility is related to the length of the chain. The bigger the chain is, the less likely that that polar or oxygen piece is actually going to matter. So small aldehydes, small ketones dissolve pretty well in water. Large aldehydes, large ketones don't do so well. And we can see that the break-even point's about in the same place. So with aldehydes, somewhere around 4, we're pretty good. 5, we're not so great. 6 doesn't dissolve. Same thing with the ketones. Now, ketones don't start until 3 with acetone, but acetone is soluble, butanone is soluble, pentanone kind of soluble, hexanone not soluble. And if you roll it back to when we talked about alcohols on Tuesday, we saw it was pretty similar. The crossover point for alcohols was 4. The crossover point for aldehydes and ketones are 5. So again, very similar kinds of properties, and it deals with the same kind of thing. We're talking about the impact of oxygen on the polarity of the substance. Let's look at some common aldehydes and ketones. So acetone is probably the most common common ketone that we're familiar with. Acetone is used in several commercial products, in particular for solvents. So we know it most commonly as nail polish remover. That's usually a solution with acetone and a little bit of water. But we can also see acetone used for things like paint thinners, cleaning fluids, that kind of thing. Probably the most common aldehyde that we are at least familiar with is formaldehyde, methanol. And that's because it has a very common background as a biological preservative. Depending upon the field, it's becoming less and less used as that kind of a preservative because of some of the biological effects that it has on you as you use it, but it is still out there. And again, depending upon the application, it's still commonly used. Speaking of formaldehyde, we know that it can exist in a lot of different ways. In its natural state, pure formaldehyde is actually a gas. But it can easily exist in solid and liquid states as well. In the solid state, it forms kind of this waxy polymer called paraformaldehyde, where basically we take that formaldehyde and we get it to react with itself to make this really, really long chain that takes on kind of a waxy kind of appearance and feel. We can also find it in the liquid phase in the form of a solution. If we put formaldehyde into water or into methanol, we get a solution called formalin. We can also take paraformaldehyde and dissolve it in water and create a solution that way. We can also find formaldehyde in a lot of different kinds of materials. So insulation, carpeting, plywood, byproducts of combustion processes. What's happening primarily there, especially in those first cases, those are all polymers usually. So the if you're looking at like fiberglass insulation or carpeting, there's usually a polymeric kind of quality to them in terms of how they're made. And formaldehyde is one of the byproducts of that processing. And so, what was that? They don't use it now it still finds its way, especially into some cheaper materials. But yeah, it's not supposed to be there. You're right. In laboratory settings, we tend to use formaldehyde for tissue preservation or as a disinfecting tool. There are some other less common uses. So, one that you're probably a little more familiar with, embalming fluids have formaldehyde as one of their primary bases. We also see it used in plywood adhesives. We can also see it in some textiles and as a fumigant. But again, the links between formaldehyde and certain kinds of nasty diseases and ailments have made formaldehyde use something that is generally tried to get away from as much as possible whenever possible. Now, that doesn't mean it extends to all fields, because in some fields, you really can't get around it. There's not a better alternative. But, if you go to a biology lab nowadays, in my parents' generation, and even into part of my generation, biological samples found in a high school classroom would all be in formaldehyde. You would use formaldehyde if you're going to do a dissection to preserve the sample. That's not the case as much anymore. There are other better ways of doing it that still do the preservation for long-term storage without the nasty side effects of formaldehyde. But again, that's not every field. Not every area is able to go and do some of those alternatives for different industrial standards. There is a note in here. This note is not in your textbook. But talking about glutaraldehyde as opposed to just formaldehyde, glutaraldehyde is one of those alternatives that is out there. It is more effective in terms of disinfection. What it does is it works on proteins and fixes those proteins in a more rapid fashion. From a chemical reaction standpoint, it is not as dehydrating as formaldehyde. It does not have the same affinity toward water. And because of some of these, it's able to disinfect at lower concentrations and create more cross linkages, which make for more stable, stronger bonds. And as a result of all of those things, it does have a tendency to have a better penetrating quality than formaldehyde does, because it's able to get in without driving out so much water. It doesn't get diluted by the water nearly as effectively. And so it's able to seep into the tissues deeper as a result. Okay, so the last section here in chapter 12 is all about chemical reactions of all of these things that we've talked about this week. So looking at alcohol styles, the aldehydes and ketones, what kinds of common reactions do we see? What are the hallmarks of these reactions in terms of how do I recognize that this is happening when it's happening? So similar to what we were talking about at the beginning of this week, the idea of a hydration reaction, water bonding across a double bond in the presence of a strong acid, and basically undoing a double bond and turning it into a single bond. Well, we can reverse that process. if we add enough heat. So with heat and the presence of acid, what we can see is that the hydrogen hydroxide, so the hydrogen hydroxyl, the H and the OH, basically we can chop them off of adjacent carbons and form water. So the reason it's called a dehydration reaction is that it is pulling water off of the chain. So it's kind of weird to think of it that way, because in the end we get water at the end of this. And so you would say to yourself, well, that doesn't sound like a dehydration reaction. That sounds like a hydration reaction. We're getting water in this process. We're looking at it from the standpoint of the molecule. The molecule is losing a water molecule. And in the process, those adjacent carbons where we've plucked off the hydrogen in the hydroxyl group, they reform that double bond that was there. And so dehydration reactions, again, under high heat with acid, can help us to form alkenes out of alcohols. And again, this is basically the reverse of the process that we saw earlier this week with hydration reactions, where we had an alkene and we turned it into an alcohol just by adding some strong acid. The main difference here is the heat. You can't do this one without the heat because the reaction itself requires a good bit of heat to go. To get a better understanding of all that is going on in these reactions, we have to have a good understanding of the terms oxidation and reduction. Now, to a chemist, oxidation and reduction bring up a whole host of different kinds of chemical reactions that are going on. But for organic chemistry, we can kind of take most of that down to what's going on with oxygen. Oxidation reactions are going to increase the number of carbon to oxygen bonds. And they're going to do that by either we're adding oxygen to the molecule or we're removing hydrogen, which allows for an extra bond to occur between the carbon and the oxygen because now there's a space opened up. That's what oxidation is. Oxidation increases the number of carbon to oxygen bonds. Reduction is the exact opposite process. When we are reducing the number of carbon to oxygen bonds. Sometimes that can be from the result of we're removing oxygen in some kind of way. Other times it can be just from the addition of hydrogens into the molecule itself. If we add hydrogen, that means that there are going to be less bonds available for oxygen. And so we can kind of follow a pathway here where at one end, the most reduced form, the form that has no oxygen in it whatsoever, would just be our alkane. And on the other end, the most oxidized form, where we've got 3 total bonds to oxygen, would be something called a carboxylic acid. Now, we haven't talked about carboxylic acids yet, but basically think about the marriage of an aldehyde and an alcohol on the same carbon. So I've got an end carbon that has a carbonyl and a hydroxyl group on it at the same time. That's what a carboxylic acid is from a structural standpoint. We'll get more into the naming and all that other stuff with it later on, but that's how we can recognize it. Basically, it's the marriage of an aldehyde and alcohol on the same carbon. But in between, we can see that we can go through a series of processes to either add oxygen bonds in terms of oxidation or remove oxygen bonds in terms of reduction. And so that's primary kinds of reactions that these compounds go through, are these oxidation reduction reactions where we can interconvert between one and another. So let's take a look at an example. Primary alcohols. So again, remember what a primary alcohol is. This is an alcohol group attached to a carbon that is attached to one other carbon. So these are the carbon, these are the alcohols where the alcohol is on an exterior carbon. If that bond, if that molecule goes through an oxidation process, because it is a primary, it's an exterior carbon, that oxidation is going to create a carbonyl group. And since that carbonyl is on an end carbon, we're going to end up with an aldehyde. Because there's really no other option for what it would do. Can't do really anything else. If it's on the outside, all that it can do to add an extra bond is to create a double bond. And since it's on the outside, an aldehyde would be the result. If an aldehyde undergoes an oxidation process as well, we can't make 3 carbon to oxygen bonds between the same 2 atoms. So oxidation would only come from the addition of another oxygen atom from somewhere else. And so the net result there would be a carboxylic acid, because that third bond would have to come from some other compound, some other molecule. What about secondary alcohols? What if I have, instead of an exterior alcohol, what if I have an interior alcohol? What if I have an alcohol that's in the middle of a chain, bonded to 2 other carbons? Well, the same thing would happen. That interior oxygen to carbon, well, when we oxidize that, it's going to drop off that hydrogen and form a double bond. But because that double bond is in the middle of the chain, we're not talking about an aldehyde anymore. Now we're talking about a ketone. Okay, so that's primary alcohols. Secondary alcohols. Remember, there were tertiary alcohols. Alcohols where that hydroxyl OH group is attached to a carbon that's bonded to 3 other carbons. Well, in that case, that can't be oxidized. The reason it can't be oxidized, that carbon is already bonded to 3 other things. And its 4th bond is to the oxygen. Where is it going to create an extra bond to make a double bond to oxygen? It can't. So it doesn't. So tertiary alcohols, they don't get oxidized. They're actually kind of protected from oxidation by the fact that they are bonded so heavily carbon to carbon there. All right, we're going to take a little bit of a side trip here. And we're going to talk about some chemical testing. And the reason we're going to talk about chemical testing here is because, one, you're going to see it in lab. And two, there are some really specific chemical tests out there that you can easily do in a laboratory that would help you to tell the difference between alcohol, aldehyde, and ketone if all you were given was just a colorless liquid that you didn't know anything about. Now, obviously, if we tell you that it's this, you know, there's not a whole lot that you can do to undo that. But if we're just giving you, hey, here's this colorless liquid, can you tell me if it's an aldehyde or a ketone? There are a couple chemical tests that you can do that would help with that. We'll start by talking about methanol poisoning. Why is methanol so dangerous? Well, inside your body, that methanol gets converted. It can be oxidized. And the oxidation products of methanol are first and foremost formaldehyde, which we already know formaldehyde is not something we want swimming around on our insides, at least not while we're alive. And the second oxidation product is formic acid. And formic acid, like any other acid, is not something that you just want hanging around your insides. There are very specific parts of your body where acid is supposed to be. And if it's not one of those places, you don't want it there. So methanol poisoning is a serious matter because it can very quickly react and oxidize inside of your body. Now let's talk about those tests. So the first test we're going to talk about is called Tollens test. Tollens test is a test that is used to help to differentiate between aldehydes and ketones. How it works is that the Tollens reagent contains silver ions. Those silver ions will oxidize in the presence of an aldehyde. And so what will happen is that the silver ion will oxidize the aldehyde, turn it into an acid, which is what we were just talking about. And the silver, which is going to take those electrons from the results of that conversion, it's going to turn it from a solution of silver to silver metal. You'll end up getting a silver mirror forming inside of the test tube. So the reason it works for aldehydes but not for ketones is because ketones don't get oxidized further. Because again, where would that hydrogen come from to create that extra bond? It's already on the interior of the chain. It's got bonds to two carbons and two bonds to oxygen already. That carbon's full. It can't accept another bond to oxygen. So ketones don't oxidize, but aldehydes do. We know that aldehydes can get converted into acids. So Tollens test takes advantage of that and helps us to separate the two substances from each other. Benedicts test. Benedicts test uses the same kind of an idea. Here we've got Benedicts reagent. Benedicts reagent contains copper 2+. Copper 2+ is a blue solution. Where it can be helpful is if we know we have an aldehyde that has a hydroxyl group next to it, Benedict's reagent will react with that aldehyde to turn it into an acid. And while we really can't see visually a difference between the aldehyde and the acid, the Benedict's reagent will turn from a blue solution to a red solid. So the nice thing about these tests, they're very visual. and it's really pretty hard to get an ambiguous result. You know, we know the difference between a blue solution and a red solid. We know the difference between a colorless solution and a mirror, which is basically what the Tollens test did. So the nice thing about these tests, very visual, very easy to see whether we have a positive result or not. Simple aldehydes, ketones aren't going to have those because they're not going to have that adjacent OH group to help react with the copper and form that solid. So visually, that's the difference between them. Copper 2, very nice kind of sea blue color. Copper 2 oxide, or copper 1 oxide rather, Cu2O, brick red. Kind of hard to see, but if you look closely at the picture, you can see down here at the bottom, there's definitely a solid there. And if you were to let that settle, that red solid would just continue to settle down to the bottom. All right. In the interest of our time, I have 2 whole minutes left. I'm not going to try to go through every aldehyde and ketone reduction reaction in that time. I will save that for Monday. As far as like, you know, what's in the book about this, it's page 419 and the top of 420. It's less than a page of text. But we've got a lot of example problems that are going to go after it. So I'll move that to Monday. You should, with everything that we've talked about, you should be able to do pretty much all of both of the post lectures for chapter 12. There's really not a whole lot left here to talk about other than just this one subclass of reactions. So start working on those things, start kind of getting your head around those. Spend a good bit of your time this weekend, though, thinking about that nomenclature quiz. Hopefully we've done enough practice between here and post-lecture that you should feel at least a little bit better than you did last week. Maybe. The looks on your faces say, no way, we're bombing this on Monday. Have a great weekend.